Hello, I welcome you all. The problem reads, rod OA rotates counterclockwise with a constant angular velocity of theta dot equal to 5 rads per second. The double collar B is pinned together or is pin connected together such that one collar slides over the rotating rod and the other slides over the horizontal curved rod, of which the shape is described by the equation r equal to 1.5 in brackets 2 minus cos theta feet. If both collars weigh 0.75 pounds, determine the normal force which the curved rod exerts on one collar at the instant theta equal to 120 degrees. Neglect friction. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Benam. What are the catch words? This is in the horizontal. It's a horizontal curved rod, and by this we assume it is in plan view. Okay, so the weight of the two collars will be facing or will be pointed inside the screen. Okay, the weight of the two collars will be inside the screen. Okay, because we are assuming this, or it has been stated here. Those we could have stated maybe horizontal plane, but they are telling us to say one collar slides over the rotating rod and the other slides over the horizontal curved rod. So we are assuming this is in horizontal plane. Okay, plan view, or we can say horizontal plane. Okay, plan view or horizontal plane. This is what we are saying. All right, so let's draw the free body diagram. So we are going to have a normal force in one of the collars that is in contact with the curved rod. So here we expect a normal force. Tangent to that line. Okay, tangent to that line. We expect a normal force. Tangent to that line. Okay, this is tangent, right? So at that point, we've drawn the line tangent. This is normal or perpendicular. Okay, so something like this, right? And then we do have also a force perpendicular to the arm. There'll be a force there. All right. Okay. What else? Then we do have this is one coordinate we are calling the radial, and we do have another coordinate there we are calling theta. So let's say this angle here is psi, and then this one here is alpha. Okay, right? So we're going to have components. So this one is our normal force, and this is our force, okay, being applied by this rotating arm OA. This is the coordinate radial or r, and this is theta. So we'll have two components. From the normal force. So we'll have one component in this direction like so. All right, maybe we take it up to there, that one, and then we'll have another component in that direction like so. Okay, So let's say this one is n sine alpha, and this one here is n cos alpha. So I think this is it for now. Let's write down what we have. So we said this one is psi, this one. Okay, so tan psi is just equal to r divided by the r, the theta. Okay, and our r is just equal to 1.52 minus cos theta. Okay, all right, and then our dr, the theta, is just going to be equal to 1.5, and then the inside there, of course, 2 becomes 0. And then here cos theta, derivative of cos theta is minus sine theta, so minus and minus cancels, therefore this just becomes sine theta, which is just equal to 1.5 sine theta, and our theta we've been told is equal to 120 degrees. So let's work it out. So we know now that tan psi is just going to be equal to r, which is just 1.52 minus cos theta divided by 1.5 sine theta. So we are evaluating this at theta equal to 120 degrees. So this just becomes equal to, that's 2 minus, so 1.5, 2 minus cos 120. So this gives us a 3.75 divided by 1.5 sine 120. And this one, so we can divide all this. Okay, right, I'll divide them together. Therefore psi, making psi subject to the formula, I don't want to round off anything. Okay, so psi therefore just becomes equal to 1.5, 2 minus cos 120, okay, divided by 1.5 sine 120. Then tan inverse of that, we have 70.89 degrees, and then our alpha is just equal to 90 degrees minus psi, which is just equal to 90 minus 70.89, and this gives us a 19.11 degrees. All right, so we have this. Let's go ahead and find the inputs, r dot, r double dot, and the rest that we are going to use for the acceleration in the r and theta direction. So this is given, the one describing the path. Okay, and therefore r dot is just going to be equal to this. R dot is a derivative of r with respect to time, so we factor out 1.52 becomes 0. Then derivative of cos becomes minus, therefore positive, so we'll have a theta dot sine theta, which is just equal to 1.5 theta dot sine theta. Okay, here we are using chain rule. Okay, so now we are going to find r double dot, which is just the second derivative of r with respect to time. So we're going to work on this one here, and we have two functions here, theta dot and just theta, so we use product rule. So I'll factor out 1.5 like so. I'll make one constant, remember product rule, while the other one remains constant. Okay, then I'll say plus, then I'll move to the next one. So we'll have theta there dot, which we're making constant, then theta dot cos theta like so. Therefore r dot is just equal to 1.5 theta double dot sine theta plus theta squared cos theta. Okay, great. And then we do have theta itself, which we know is 120 degrees. And then we have theta dot, which is equal to 5, and it is constant. And because it is constant, we expect theta double dot to be equal to 0. Right, so let's find these values at 120. So r at theta equal to 120 degrees. At 120 degrees, this will just give us as 1.5, 2 minus cos 120. So this is a 3.75. Okay, this is a 3.75. And then r double dot at theta equal to 120. We have 1.5 times 5 times sine 120. So this gives us a 6.4952. All right, and then no, this one is theta dot. This is theta dot, not theta double dot. This is the one I was working. Then I have theta double dot at theta equal to 120. So this part is 0. This one here is 0. So I will have the following: 1.5 times 5 squared cos 120. Okay, this is just equal to minus. This is equal to minus 18.75. I guess we have done everything. These inputs, we need them as we calculate the acceleration a theta and ar. So our ar is just equal to r double dot minus r theta double dot like so. Therefore ar is just going to be equal to we have all these values there, you can just feed them in. So we have minus 18.75, and then minus r, we said is 3.75 times 5 squared. So this we get a minus 112.5. Okay, minus 18.75 minus, that's r 3.75 times 5 squared. Okay, and then we have a theta, which is just equal to r double dot plus 2 r dot 2 r dot theta dot. Okay, what do we have? Let's plug in all the values. We already have them. So our r, in fact this part here, this one goes to 0 because theta double dot is 0, so it's just 2 by 6.4952 times 5. So we have a 64.952. Right, so let's apply the equations of motion. So we have summation of forces in the r direction equal to MAR going up in our reference. In that direction we have minus n cos alpha equal to MAR. So we have minus n cos alpha, and alpha we calculated it as 19.11 degrees equal to m. Then here we are just dealing with one collar. Okay, the normal force which the curved rod exerts on one collar at this instant, and one collar weighs 7.75, and we are dividing it by the acceleration due to gravity, that we convert it to mass, then times the acceleration in the other direction. Alright, negative and negative cancels, and therefore our n is just going to be equal to 0.75. Right, I'm calculating. Can grab your calculator also and do the calculations. So this gives us a 2.77 pounds, and this is in the direction, it is in this direction. We can also compute F, though we've not been asked to do so. So we can say summation of forces in the theta direction equal to MA theta, and going in this direction being our positive. What do we have? We do have n sine alpha plus F equal to MA theta. Our n, we just calculated it, is 2.77 sine 19.11 19.11 degrees, and this is plus F equal to m, which is just 0.75, divided by the acceleration due to gravity in feet per second squared, times a theta, which we calculated as 64.952. Therefore our F is just going to be equal to, so we have 0.75. You can calculate that also. Grab your calculator so that we can compare the answers. Okay, right, so my force is just 0.6060 pounds, and it is in the same direction. Let's now outline them. So there we go. We have the n, which is the normal force, and then we do have the F. Alright, I think this is about it, and I hope this video was helpful, and if it was, give me a thumbs up, like my video, and share it. Bye bye, and see you in my next screencast.